Dr. Nitin, we can start the talk.
Fine. Yeah. Okay. Yeah. Good evening. Yeah. Welcome back. Yeah. So yesterday, what we did is that we did how optimization techniques can be used for nonlinear system identification is what we did. Okay. So we looked at this Hammerstein model, Wiener model, NLN model, or this different type of models we looked at. We looked at some application cases. Okay. So now today we are looking at applications to audio signal processing. Even though it is application to audio signal processing, we are only specifically looking at one application, which is active noise cancellation. That is the only application we are looking at. Because I think there are other applications which are coming up. I think tomorrow there are some application in hearing aid, which is there tomorrow. Okay, fine. So let me explain what is this thing called active noise cancellation or active noise control. So you would have heard this word active noise control because there are ANC headphones. Okay, so you will keep hearing about ANC headphones, active noise cancellation headphones. Now, in this talk, what we are trying to do is we will try to understand what is this problem statement, how this is an optimization problem, how this could be formulated as a multi-agent optimization problem. These are the three things which we are going to look at. So to explain, what I have taken is, I have considered a tube, duct is a tube, and I have a noise source at one end of the duct. So you can assume that you have an air conditioner in your room, and then there is a compressor which is outside of the room, and some noise which is there outside is coming to the inside. Okay, so there is some noise which is there in the outside, that is a noise source. That sound is passing through this duct and it is reaching the inside of the room. And my objective is I want a low noise zone in the inside of the room. Okay, so my objective is to not to switch off that AC and then cancel the noise. The AC will still be there, noise will still be produced, but now can I have a low noise zone inside of the room or at some other location is our objective. Okay, so if I want to do this, what I should do is I should first know what type of noise is coming from the outside. So what I do, I take a microphone called as a reference microphone. One microphone I am keeping near the source of the noise. So I am taking what? I am taking one microphone and keeping it near the source of the noise. That is going to give me a signal X of it. Okay, so that mic is giving me an output which is X of it. Okay, fine. Now what I am trying to do is, my objective is there is some sound which has been produced and that sound is coming inside. That's a noise for me. I want to cancel that noise or remove the noise. To remove that noise, I generate another sound deliberately and try to see can I have a destructive interference or not. So because I need to generate a new sound, I have put a loudspeaker over here. So this is my loudspeaker over here. So this is a loudspeaker which I am putting into my system. It's an extra loudspeaker which I am putting into the system. Okay, so I have one microphone which is measuring what type of sound is coming from outside or from the noise zone. Then I have a loudspeaker which I am going to see if I can produce a new sound which is going to interfere with the sound which is coming from the outside and see if I can somehow cancel it. So if I want to know whether my sound is cancelling or not, I should measure what is the sound which is inside of my room. So I should put another microphone, which I am calling it the error microphone. So what I did is I looked at the system. System has one mic which is outside. Understood. There is a loudspeaker which is there somewhere in the duct, and there is a microphone which is inside to measure how much noise is getting cancelled. And the signal which is measured by that is called the error signal. Now, similar to system identification, what I am trying to do is I am going to have an adaptive filter. For example, an FIR filter. So what is this adaptive FIR filter trying to do? So I am going to have some delays, some multipliers, some adders. This is my adaptive FIR filter, and depending upon what value of multipliers are there, the adaptive it's not clear. Is it better now? Is the sound better now? Okay, fine. Yeah. So what I'm trying to say is I have a mic which is outside, I have a mic which is inside, I have a loudspeaker which is going to create that anti-noise, but the loudspeaker is controlled by an FIR filter, for example. That FIR filter is like what? This is my FIR filter. So the FIR filter contains what? Some multipliers. So depending upon what is the multiplier value, your loudspeaker is going to produce different outputs. Correct? That means if I can somehow control this FIR filter or manipulate this FIR filter or modify this FIR filter parameters, I could create different sounds from the loudspeaker. And when different sounds are generated, I could say that I want to minimize maybe a function of error and use that to update my controller. Understood? This is exactly like what we did yesterday. So what are we trying to do? We have a noise source. So when the noise is coming inside the room, I am deliberately putting a loudspeaker and I am telling the loudspeaker you produce some new sound, but it should not be any random sound. What I want is the loudspeaker should produce sound in such a way that the signal E, the signal at the error microphone or a function of that has to be minimized. Now I have an optimization problem. Similar to what we were doing earlier. We have an optimization problem. Understood? Fine. Yesterday, if you remember, we wrote this equation E of n is equal to D of n minus Y of n. We wrote something. Understood? So, if I want to develop algorithms for doing this in a conventional adaptive filtering method, what I should do, like we did yesterday, is that convert physical systems into models by using a system identification process. Okay, physical systems into model in the sense what? I have this x of n signal is there. X of n is going through this FIR filter. It is giving an output, but this output at this position A is an electronic signal. Then it is passing through where? After passing through, this is passing through this air and it is coming over here to reach position B. So A to B is a physical path, like what we saw yesterday. So there is a physical path between A to B. So I could do a modeling and replace that by another filter. So I replace that by another block called S of n, which I called the secondary path. So the output of that will be this output I call it y of n. This output I call it ys of n. And then there is some signal which is coming from here, which I call d of n. They are either added together or getting subtracted to get my e of n signal. Okay, this is how the problem is getting formulated. Understood? In a traditional form. But we don't need to go there. We will be able to solve it in a much better way. I will tell you that. Okay. So this is the idea of this. I will explain in another application, then I think it should be very clear. So if you want to understand and see how ANC is working, there is this beautiful video. You can in YouTube you can search "You Can't Unring a Bell, GE and Impossible." Okay, there is a 3-minute video where it explains how an ANC is implemented in a real life. Okay, so I'm not showing it here. You Just search for this and you will get a video, 3-minute video. Just see that. It will be a very good explanation of it. So what are the major applications? Major applications are ANC headphones. So you will see this Bose headphone. So many different companies are coming with so many different types of headphones where noise cancellation is happening. Okay, let me explain. Let me draw a diagram of how an ANC headphone could be working. Okay, we don't know how exactly it is working, but based on our understanding of the first diagram, we could somehow draw a possible diagram for this. Okay, so suppose this is the cup. Okay, and what I want is I want to do noise cancellation and I want to also play music. Okay, so if I want to do noise cancellation similar to the earlier diagram, what I should do, I should have some microphone which is going to pick up that signal from outside or the noise from outside. Then it should pass it through some filter, suppose a air filter. Then after that, it should play it through a loudspeaker which will produce some sound. And then it should measure how much is the sound level or inside the headphone. So I may also have a microphone inside of the headphone which is going to measure how much noise is there and how much noise level is remaining, and I could create an adaptive filter which could reduce the noise inside. So this is one possible formulation. Okay, so I am not explaining this because this could be part of an adaptive filtering what you can say course. Okay, because here we are going to use a very different method for doing noise cancellation, not the traditional adaptive filtering method. Okay, fine. Another application which has come is in cars. So they are using what you can say active noise cancellation inside cars to reduce noise level inside the cabin, to reduce road noise. So many papers have come, so many applications are there for that also. Okay, now let us see how we can solve this problem and how it is different from a system identification problem which we did yesterday. That is what we are trying to look at. Okay, fine. Now what I am drawing over here is an equivalent diagram for the first diagram which is there, the duct diagram which is there. So this is an equivalent diagram for this diagram where I have one box over here which I called the primary path. What is this primary path? Is this point C to point B is a physical system, and I am doing algorithm development for a physical system. So whenever I am doing algorithm development for physical systems, what I should do? I should convert this physical system into a model. That model could be an FAR filter or a neural network or anything like that. So this P of Z over here is a model of that path from where to where, that path from C to B. That path from C to B is given by P of Z. This path from A to B is given by which one? S of Z. S of Z is that path. And this is my adaptive FAR filter. Now what I am seeing is I have now an equivalent, a digital equivalent of whatever was happening over there in the other diagram. In the schematic, we had some signals which were mixing in the air. Means where is noise cancellation happening? Noise cancellation is happening in the air. There is already a sound in the system. You are deliberately producing another sound to the system, and both the sounds are getting mixed together, and you have an error signal, and that error signal is what is going to be minimized. What is going to be minimized? Okay, fine. Now, if you see what we were doing in a system identification, let's look at that again, and then we will understand how this is different from that. What were we doing in a system identification? In a system identification, what we were doing is you have a nonlinear system which has to be identified. And we are saying it has a nonlinear block first and a linear block second. Because the system is a combination of N and L, what we could do, we could use an NL in the model also. We could have NL in the model also. We said we have some N. Some N can be a flan. Some L can be an FIR filter. This flan has maybe some 50 parameters to be estimated. This FIR filter has some 20 parameters to be estimated. So I have some n number of unknowns, 50 unknowns over here, 20 unknowns over here, total 70 unknowns to be estimated. So I generate a random vector of 70 values and put that random values for 50 for the flan and 20 for the FIR filter. No problem. Then what I could do, if that was the model, means that was one of the possible models, I could estimate the response of that model for a given set of inputs, correct? So if I apply 100 inputs to the physical system, system will give me 100 outputs over here. If I apply the same 100 inputs to the first version of the model, what I could get? I could get 100 outputs of the first version of the model. I could generate an error signal, which is also 100 errors, 100, for example, 100 errors. And I could find the mean of the square of the error and say that is the fitness for that particular model choice. That is the fitness for that particular model choice. Similarly, I could have another 50 random values for the nonlinear part and another 20 random values for the linear part, another 70 vector. So I can have n such possible models or possible these vectors which can go into the model. N such possible models can be there. And so, for example, if I am doing a PSO, I will have this will be particle 1, this will be particle 2, etc. particle n. So each of the particle corresponds to one fitness value, correct? Each of the particle will correspond to one fitness value. And I have n such fitness values. I could run an optimization algorithm and tell you find out which is the best possible 70 values, or we are searching in a 70 dimensional space to find out which point in that 70 dimensional space will give me the best possible solution for this particular problem. And that vector which we are estimating out of this search using a multi-agent optimization is equal to the parameters of your final model. So how my final model will look like? Final model will have 50 parameters which are going to the fan, and I will have 20 parameters which are going to the FIR filter. Okay, this is going to be estimated using this entire process. So for estimating this, what I needed, what I did, I gave 100 inputs to the system. For example, I found out 1000 output of the system. I compared that 1000 outputs with the response of the first model, second model, third model, etc. And I had this so many summation blocks to find out the n number of different errors, and then I could formulate the problem and I could solve this problem. Okay, this is how it is going to be done in a system application. But that problem is not very easy in an ANC problem because of multiple reasons. I will tell you why that reason is there. So what happens is I have sound which is produced from here and the sound is passing through here. It's going like this. Okay. And now my objective is similar to the nonlinear system identification which we did earlier. We want to formulate this problem as a multi-agent optimization problem. So ideally what I should be having is I should be having n number of possible solutions for the controller, n number of possible solutions for the controller, give this input to all the n number of possible solutions, and then find the error. But the problem is, unlike the previous case of nonlinear system magnification, where we were having all these summation blocks which we are calculating algorithmically, these subtractions are done algorithmically, I cannot do that in a ANC system, because for the ANC system to do this summation means d of n minus phi s of n, as I wrote earlier. This summation is not a summation. It is a summation which is happening in the air. Okay, it is not a sum block. It is a virtual sum. It is a sum which is happening in the acoustic domain. It is not a sum which is happening in the electronic domain. So in the software, I cannot have n number of sum blocks and find out n number of errors. That is not possible. Second is, for this signal to go into the air, I need a physical system. That physical system is a loudspeaker, because only through a loudspeaker I can interact. My algorithm, my PSO, if I want to find its fitness value, that vector of parameters should give me an output. That output should go into the physical world, and the physical world interaction is with the loudspeaker. And I am not, if my population size is 100, I cannot have 100 loudspeakers, because I wanted to use an evolutionary algorithm to solve it. That is not a solution. Understood? So we need to have a solution by having minimum hardware, and then I should be able to use this. Understood? So you cannot replicate a nonlinear system identification scenario in an active noise control scenario because of these reasons. First is, you need an actuator to go into the physical domain. You need a microphone to measure how much is the error in that system. That also I need. Third is, you cannot have a summation block, because the summation is happening in the air. These are the three type of scenarios which are going to be there. So I cannot formulate it as an earlier case, but if I can formulate it as an optimization problem solved using a multi-agent optimization algorithm, that may have a lot of benefit. One benefit is, if you see here, I have written something that this signal, so there is this, I think let's not go there. I think it's okay. Fine. There is some advantage. So the one advantage, I'll just mention what is the advantage. Let's not go why that advantage is there. So this modeling of the secondary path, which is necessary, modeling of the secondary path which is necessary for solving this problem, is not needed if I use a multi-agent optimization. That is the main idea which is there. Okay. That is the main idea which we have to use. Okay. So one possible solution to this problem is that I could use a system like this. What is this system? This input is coming from the mic. This output is going through the loudspeaker. And some sound is going from here to here. So what I do is I take a set of inputs which are coming from here. You have a demultiplexer, and you pass it through the first set of weight which corresponds to the first particle. You pass it through a model or a filter where the filter values, the filter multipliers correspond to the position of the first particle. Then you pass it through a multiplexer and pass it through the loudspeaker. So what has happened is, you have sound which is continuously coming. The noise is not stopping. The noise is continuously coming. Okay. So when the sound is continuously coming, you take n number of samples, maybe 100 samples. You pass it through a controller which corresponds to the pass it through a controller which has multiplier values equivalent to the first particle. So P1 corresponding to the first particle. And then you estimate the error here, E of n. So now I can say this error is due to what? This error is due to some sound which is coming from the noisy area, and the cancellation is happening because of a controller which has multiplier values corresponding to P1. So I have got some error value which I will consider as an event or a set of events. Then after some time what I will do, I will move this to the second path. I will get an approximation of E. Why this is not an exact value of E is because for estimating the first error, I had used some sound which was coming from here, and when I am estimating E2, I do not have the same sound there because that sound has already gone. Some new sound is coming. So the D of n which was used to find the first error is not the same as the D of n which is used for finding the second error, because this is a real-time system. The signal just keeps going. Understood? But it is an approximation. Understood? And I do all these things over here. I find E1 to ER in this case. After that, I again start with the first. So what happens is, for example, I give 100 inputs to the first weight set to find E1, next 100 to find E2, another 100 to find ER. I have got one estimate of these E's. Now I run the algorithm, update the positions P1, P2, etc. Now I give the next. So in terms of timeline, if you see, this is the 0th point, 100 samples, 200 samples. Suppose there are 50 such particles are there. So 5,000 samples. Okay. At the end of 5,000 samples, your E1 is calculated, E2 is calculated, now E50 is calculated. Now when I go to 5100 samples, I again calculate E1. Now I go to 5200 samples, I calculate E2 and I keep on continuing. Understood? So I will use these first 5,000 samples and these 50 E's to update the position of the particles. I am going to use E1 to E50 to update the position of the particle. Now when I am starting from 5,000 onwards to the second phase, I am going to apply the input signal. This X of n signal is going to be applied to filters which are at the updated position, because one generation is already over, correct? Or one full iteration is already over, and you keep on doing it. Understand? This is how it is going to be formulated in an ANC system. So the advantage is that I don't need to create that secondary path model which I told earlier. Okay, if I get time, I will try to explain. I don't need to use that. That is a very big advantage in terms of active noise cancellation. Okay, this is how it is going to be. Fine. Let me explain how this can be experimentally done, but not the PSO1. PSO1 we have not done. Okay. Let me give you another example of an ANC application, which is called an active headrest system. Active headrest system means you are using an ANC headphone, your noise is getting cancelled, that's okay. But then you want the user to wear the headphone. But now, can I have noise cancellation for a particular user without the user wearing a headphone? That is called an active headrest system. Headrest system means, for example, in the car case, I could be doing noise cancellation inside the headrest of the car. because I don't want people who are using the car to wear a headphone and then do noise cancellation. Then that is of no use to me. So if my user is leaning towards the headrest, if your head is towards the headrest, you will feel that the noise is cancelled. If you are away from the headrest, you will feel that noise is not cancelled. That is my objective. Now, can we do that is the problem. So this is one such experimental setup, diagram of an experimental setup, where what we are saying is that I have three different noise sources which are there. So these are similar to engine noise or some other noise which is coming from outside. So these are the sources of noise which are there. I am putting three microphones near the noise source, because for ANC to work, what I should do? I should measure the reference signal. So I am putting microphones near the noise sources. So I have three such microphones. Then to cancel noise, what I should do? I should pass it through some filter and then play some sound. So this is the controller and controller. Means behind every ear, behind both the ears, I am going to keep a speaker. But that speaker may be inside the headrest. Okay, so you may not even notice that there is a speaker there. So what we are saying is that you have two speakers. So this is the ear. Okay, behind the ear on the headrest, I have two speakers which are going to be there. That is going to create the anti-noise signal which is going to be created. Now I should also know whether the noise is actually getting cancelled or not, or I should also have an error microphone, correct? Because I should know whether noise is cancelling or not. So these are my error microphones. Okay. So these are microphones which is going to tell the controller how much it should produce new sound. Correct? Because this controller is like a loop. So this controller is going to produce new sounds. So how much new sound is going to be produced, what frequency, how it is going to be produced, all of those are going to be decided or controlled by the error microphones. So these 1, 2, 3, 4, all of them are error microphones. So now my objective is what? So I have an E1 of n signal, I have an E2 of n signal, I have an E3 of n signal, I have an E4 of n signal. I could say I will tell my algorithm to minimize E1 square plus E2 square plus E3 square plus E4 square. This is now an optimization problem, because I am telling the algorithm you minimize a summation of all the errors. E1 square has to be minimized, E2 square has to be minimized, E3 square has to be minimized, E4 square has to be minimized. All of them have to be minimized. And what is the outcome of it? The outcome of it is the signal which is driving the controller or signal which is driving the loudspeaker has to be changed. Has to be changed means what? There will be some FAR filter here, there will be some FAR filter here, and this values of the FAR filter or multiplier values of the FAR filter are the variables which are getting updated. So these variables have to be updated in such a way that this optimization problem can be solved. This is our problem. And because we also want to know whether inside the ear of the person the sound has reduced or not, we use something called a dummy head. Okay, dummy head is a microphone through which you can measure the performance. Okay, so this is the actual setup. So what is this setup? This is a what you can say physical implementation of the earlier diagram which I showed over there, where you can see I have this noise source 1, noise source 2, noise source 3. These are three loudspeakers which are producing maybe car noise. Okay, maybe some noise it is getting produced. Then I have this control speakers. See, this is the control speaker, two speakers which are there, which are placed near the ear of this dummy. This dummy is a microphone actually. This is a dummy head, and inside the head there are mics. So it is as if you can measure what you are hearing. So there is a mic inside the ear, there is a spinner and all these things. Then I have error microphones. So these are microphones which are placed near the ear of the listener. So all of this, the control speaker and the error microphone, can be integrated into your headrest. So the headrest system is not just a headrest, it contains the speaker and the microphone setup. Okay. And now what is happening is that I have to run an algorithm, because I have to run an algorithm. And what is the algorithm trying to do? Algorithm is trying to solve that optimization problem which I said, using some method, either a gradient descent method or some evolutionary algorithm method, some methods, but it's finally an optimization problem. And it is essentially a Simulink model which is being executed on this processor. This is a speed goat processor which has a 5 microsecond type of a latency. In the sense, it's a very fast input output. Means how the algorithm, how noise cancellation should work. How noise cancellation should work? The uh, the signals which are near the noise source, we should be picked up and given to this processor. Processor should calculate the anti-noise based on this error signal. So this error signal also should be given to the processor, correct? Based on these two inputs, the input reference signal and the error signal, this fellow should calculate an output which is given to the loudspeakers, these loudspeakers, such the noise level is getting reduced. Understood? This is the overall idea on how a headrest system can be implemented, and how we can do it in real time and see that the noise is, yeah, how the noise is going to be cancelled. Okay, fine. There is one question, I will answer it just immediately after this. Okay, fine. Yeah. So now, this is how it is going to happen, where you have some ANC off conditions. For example, for a 200 hertz signal, under ANC off, I have a particular noise level. But when the ANC is on and an algorithm is running, my noise level can be reduced. Okay, my noise level can be reduced. But this doesn't make sense for us in the sound level. So you can see this will give you a better idea about how the sound is getting cancelled. See, for example, what we did is, after doing the experiment, we measured the sound level around this dummy head using a sound level measure, normal sound level meter, to see what is the noise level at every point, like in a grid. And then we are saying, if you see here, it's 95 dB is this yellow color. So it's like 95 dB sound is around the ear of the person. Understood? When we are measuring it. And when we are after noise cancellation, when you are measuring, you can see it is like 70 dB at this point. Okay. Because the mic, the error mic was placed at that point. But in this paper, what we did is, we did a different algorithm where the zone of quiet, we call it the Z of Q. So the zone of quiet, we could move it towards the ear of the person. So what happens is, this is the region where the noise is getting cancelled. You see now the blue color. The blue color is like 70 dB type of sound, dBA. And this was 95 dBA. So that much reduction in sound, it is 70 dBA. So these are sound measures. This is not the, what you can say, this you see in the convergence characteristic, not that. Okay, because this is measured using a sound level meter. Sound level meter will give me a dB output. When they say no decibel, this much decibel sound is there, the same thing only. Okay, so we had a initial state of 90 dBA for these points in the yellow color. Then after the noise cancellation is achieved, it goes to 70 dBA. But the actual noise source is not getting off. Actual noise source is still there. So when the actual noise source is still there, algorithmically, we will be able to do a cancellation, and then we will be able to reduce the sound. Understood? This is an experimental measurement of the algorithm, but there is an algorithm, there is something called a virtual sensing algorithm is what we are using to move the zone of quiet from that outside space to near the ear. Okay, if you want to see the algorithm, you can see in this paper. So there is this paper is there. This is this one. Okay, where we are doing a performance evaluation. This is a 2023 paper in the Journal of Acoustical Society of America. This is an experimental work. There are details of algorithm and also the details of how experiment is conducted. And this setup is it here at IIT Gandhar only. We have that setup over here. Okay, so we have done this experiment over here. Okay, fine. I think one question was there. Yeah, so how do we relate ANC to an equalizer? So I can think of two types of equalizer. We can think of a channel equalizer, or I could, so in channel equalizer, what we do, uh, what we do is you have a channel and you are having an equalizer after that at the receiver side, and then you have some optimization problem formed by having this z power minus d plus minus e of n, and then you update the equalizer. Here, all of this, once the channel is modeled, everything is an electronic signal. Understood. So you are able to make a measurement of d of n and y of n, and then you are able to update the equalizer such that the bit error rate is going to be reduced. And that is what we do in channel equalization. Here what we are doing is not like that. If I draw the block diagram which is equivalent to this, I have a primary path which is producing some sound. I take this signal, pass it through my FIR filter, pass it through my what you can say secondary path, and then this is getting added or subtracted. But this entire addition is not happening in the summation. It is only a representation of it. This summation is happening in the air, in the sound. Understood? That is, these two diagrams can give you some idea about how this is different. Understood? So in an equalizer, you have a cascade of filters. There is a channel and then it is an equalizer. Okay. Here you have a controller, and then there is a cascade, but that is of a secondary path. And then you have another system over there which is going to give me an output. Okay, but because you asked this question about equalizer, let me give you an equalizer in audio to draw it. Okay, equalizer in audio in the sense, if you want to take one example, so suppose suppose you have a flat TV, and flat TV is producing sound. So where the sound will go? The speaker of the flat TV is not normally in the front now, it is in the back side, correct? So what will happen is the sound will go, hit the back, hit the floor, and it will hit you. And there are so many different paths which the sound is going to take to reach the user. So I have a signal x of n which is supposed to be reaching the user. But what is reaching the user is not signal x of n, signal x of n which has been passed through a channel or a room. Understood? So this signal x of n is going to be modified by the room before it reaches the user. So I am not going to get a very good audio at the user level. But I could solve this problem by again formulating it as an optimization problem, where I say, suppose I take the original signal x of n and pass it through an FIR filter, which is going to deliberately distort the signal. And then this sound passes and reaches the user. So what I'm saying is, I have an FIR filter which is adaptive. This FIR filter is going to deliberately distort the sound and then play it. The music is there, very good music. Very good music is first distorted. And after distortion, it is played through the loudspeaker. Then what happens is the loudspeaker is playing it through the to the outside world. Outside world will again distort it because I know the room is going to distort it. So I could control this FAR filter in such a way that this distortion offered by the room is equalized by this FAR filter. That is called a room equalization. Similar to channel equalization, but in channel equalization, if you see, the channel came first and the equalizer came later. Here you have the equalizer coming first and then the room or the channel comes later. And then what I do, I put a microphone near my user. That is already available with us because we have all these remotes with microphones. So I am able to measure the sound which is there at the user level. This signal I could use through an algorithm to update this FAR filter. Understood? So this is how an equalization can work. So there are different types of equalization. So here what I have done is a room equalization. You can just search for room equalization. You will get an idea. What we are trying to do is that there is a room. Room is going to distort the sound which is produced or which is played by the TV. So I design an algorithm which is going to compensate for that distortion by deliberately distorting the sound and then playing it through the speaker, so that a distorted sound which is again distorted in the opposite way can give me a good sound. That is called that is the idea of a room equalization. Okay, fine. Fine. Okay, so this is the major idea, but now it's not necessary that the controller which we are going to use has to be a linear controller. Okay, so similar to what we did yesterday, I could have a non-linear controller. Understood? So what I am saying is the controller which is controlling the loudspeaker need not be a linear one. It can be a non-linear one. It is okay to have a non-linear one because already the loudspeaker I said could be non-linear. Okay. So I could, for example, use a flan or maybe an A flan like we did yesterday. Understood? So I could use any of these instead of an FAR filter. It's not necessary that the controller which we are going to use in the first diagram, this adaptive controller over here, it need not be an FAR filter. It can be a nonlinear filter. It can be a neural network. Understood? And I could formulate this optimization problem such that the error can be reduced over here. Understood? So these are the type of things which we can do. Fine. Any doubt? I think already 1-2 questions were there. This I think I have replied. Are there any other doubt? Yeah. If you have any doubt from yesterday and today, you can ask now. We'll just put in the chat. Okay. And when you have time, you see this video. I will explain what is there in the video so you can understand. So what they do is they are going to do a noise cancellation and they are going to do a noise cancellation of a bell sound. So there is this bell is there over here. That bell is creating some sound. That sound is coming. And this is disturbing a baby. That's how they have formulated it. So they keep a baby here. Baby is here. And they want to cancel the sound near the baby and not cancel the sound for everybody else who is around the baby. Understood? Because ANC is a local cancellation. In the sense, wherever the mic you keep, error microphone you keep, only around that region you will get cancellation. Other regions you don't get cancellation. So what they do is that they put some sensors on the bell. Okay, it can be a vibration sensor type of thing. Understood? It need not be a microphone. It can be some signal which is correlated with that signal. So they are putting some signal, and then they are giving it to a controller, similar to the controller which you saw in the previous diagram. Then they have these speakers. These are the speakers which are there around the baby, and all of them are controlled by this controller. So this is your controller. Okay, all of them are controlled by the controller. And what is the speaker trying to do? Speaker is trying to produce some sound. Okay, and what should I tell the algorithm or the controller to do? Reduce whatever signal is there around the baby. So what I should do is, I should have some microphones around the baby's ear, somewhere near the baby's ear, and that is my error signal. And I will tell this, give that information also to the controller, and tell the controller that you move your loudspeakers, that 4 loudspeakers which are around the baby, you move your loudspeaker in such a way that this E signal which is around the baby has to be minimized. Again, optimization. Okay, so the E signal which is around the baby has to be minimized. Okay, fine. But because for somebody who is standing over here, or somebody who is standing over here, around that person there is no error microphone. So the algorithm don't know that I am supposed to cancel there or not. So the noise or the bell sound is not getting cancelled for people who are outside or around the baby, but only for near the baby the sound is getting cancelled. Understood? This is how it is going. And in that experiment, in this video, they actually show that the baby is sleeping and the baby is not getting disturbed, and you will get a very good idea about how this ANC is going to work in the real time. Okay, correct. Yeah, so that's why all our algorithms are adaptive, because I am continuously monitoring what is the environment noise, what type of noise, because it is not like you have a fixed what you can say anti-noise signal generation, because your input signal will keep on changing, your head will move. Understood? When you are wearing a headphone, all of those things can going to move, but even then the algorithm should work because it is adaptive. So every time the algorithm is always running, it is not that once you did it, it's all over. Algorithm is always running and it is looking for better and better solutions. Okay. Fine. Yeah, any other doubt? This you see, you will get a very good idea. Yeah, fine. Yeah, anything else? Yeah, I think then we'll stop here. Any doubt? If any doubt is there, you just send in chat. Fine. Okay. Okay.
Good evening, sir.
Yeah, hi.
Myself, Dr. Ila Sharma, one of the
Hi.
here in FTP.
Okay.
So,
I think we'll stop here.
yes, sir, if somebody is having any question, they can mail you also.
They can mail me.
And if it reaches to us, we will forward it to you.
Yeah, you can forward it to us. Okay. Then I will
Thank you so
reply
much,
to it.
sir, for this great lecture to us. Hope all will be benefited from it.
Yeah. Okay. Okay, bye.
Thank you. So, participant, our next expert is about to join in a few minutes. So, let's have a small 2-minute break for that.